Rick Donnelly with WSP Parsons Sprinkerhoff and myself, Josie Kressner from Transport Foundry, are recapping the presentation we made last week in Denver at the Innovations in Travel Modeling Conference for anyone who was not able to attend. So here we go. In travel demand modeling so far, the only thing we've used big data for is to calibrate or validate one piece of a travel model. We're departing from this path by building an entire model on big data. We've done this in Seattle and Atlanta, but we wanted to test it in a less complex region. We selected Asheville, and we compared this new model against the existing trip-based model in the region. We decided to make this comparison by hooking up both demand models with the same assignment model. So that's what Rick, Greg McFarland, and Lita Huntsinger, all from WSP, and myself did in Asheville. And that's what we're going to share with you today.
So we'll first start by briefly explaining the existing trip-based model in the Asheville region, and then we'll describe how we approach the demand model differently.
We've all seen this familiar four-step model flowchart with generation, distribution, and mode choice that feed into an assignment model. The most modern version of this traditional four-step demand model was built and put to use in Asheville region 2 years ago. The inputs to this model include travel surveys and zonal socioeconomic data developed by the French Broad River NPO. And the assignment model in this region was built in Transcad and is a static assignment. For context, we show here how an activity-based model fits in this flowchart. An ABM takes essentially the same type of inputs, they're just more detailed, and it estimates more sophisticated behavioral dynamics than the trip-based model. But the outputs get summed up and fed into an assignment model just the same. With this new model, we took an entirely different approach, starting with the input. We used passive data instead. We used essentially three types of passive data. We used consumer marketing data, firm data, and travel data, including origin destination data and travel time OD data and real traffic conditions. In the Asheville implementation, we used data from Epsilon, InfoUSA, AirSage, and HereMap API. We also pulled statistics about tour behavior from NHTS. Onto the demand model, there's basically two steps. We have a population synthesis and we have a discrete event simulation. The population synthesis is similar to that we use in an activity-based model. In the activity-based model, the population synthesis starts with American Community Survey PUMS data available at the PUMA level. And each household in that PUMS data is expanded and then allocated to smaller geographic areas like TAZs or MAZs. In our case, we start with Epsilon data, which is available at the household level with household address. So rather than taking household level data that's available at a large geographic area and allocating it to smaller levels, we start with very detailed, geographically detailed household information, and we pull it with the census data. Once we get the population synthesis set up, we pass that into a discrete event simulation. A discrete event simulation is a way of codifying the behavior of a complex system as ordered events along a timeline. And each event occurs at a particular instant in time along that timeline and marks a change in the state of the system. For example, one change in the state of the system would be a person leaving their home or a person arriving at work. In between these events, we assume that no change in the system occurred, so that the simulation jumps in time from one event to the next. And we train this DES using the NHTS tour pattern. Using the synthetic population in the DES, we model the same aspects of behavior that we model in the four-step or activity-based model, but with a unified simulation rather than sequential steps. And in the same way, the trip-based and activity-based model feed into a static or dynamic traffic assignment model, this demand model does as well. The output from the demand model that feeds into the assignment model, though, is quite different than that we get from a trip-based model. These types of tables shown here in the slide, such as trip production tables or link tables or different types of matrices, are the outputs that we get from a typical four-step model. With this model, we get an output very similar to an activity-based model, where we get a tour table that details each person's travel diary, essentially, for a 24-hour or 48-hour period. So here I'm showing 3 random people from the Asheville implementation, where they have person IDs and place IDs of where they traveled during that day. And these are each linkable to relational tables that include demographic and business details about each household or business location. And for example, this person left to go to work to make a simple work tour at 7 a.m. They arrived at work at 7:30 and were there until just before 5 p.m. And then they returned home and made no more tours for the day. And with that, I will pass the baton on to Rick.
Okay, thanks, Josie. I guess you would consider what we're describing to you as a proof of concept, something that when we set out, we weren't even sure how it would work. So while there's a lot of details on the concepts that we'd like to present to you that we just don't have time for, I'd like to blow through some of the proof. And that's my part of the presentation. And in fact, I'd like to kind of do it in reverse of the way you'd walk through a model. So we're going to start at the end and work backwards, looking at the traffic assignment model. Recall Josie told you that we used the exact same traffic assignment, and when we did, we created a graphical summary of the results compared to daily traffic counts, which you see here on the screen. And across the top, you see simply the observed versus estimated flows at the count locations in the model, and on the left, you see the existing trip-based model, and on the right, you see the model that Josie just described. And of course, as you look across those two plots on the top, you see they're very close. There are some outliers you see with our model, but it's important to note that we haven't calibrated this model yet. We've simply implemented it. This is the raw output of the DES, whereas the model on the left is a calibrated model. I've sort of spun the points in a different way across the bottom, where we've compared it to what we call the maximum desirable error curves that we initially started using with NCHRP report 255 and now in 765. And the idea is that you want most, if not all, of your points to be underneath the curve. And I've shown 2 curves here because I like seeing the directionality of the error. Again, there's some work to be done if we wanted to make this thing look as sharp as the trip-based model, but it's not very far off. And an important thing to note is that these look better than most models that I'm used to working with. If you're used to looking at a tabular summary, we've created one of those as well. And here you can see the vehicle hours of travel, the route mean squared error, and the percent route mean squared error by facility type, roadway type, across the region. The VHT is kind of different because of the way that tours versus trips are structured, but as you can see, the RMSE and the percent RMSE are quite similar. On freeways, you see the effect of the outliers that we just saw in the previous graph, making our percent RMSE not quite what it is with the calibrated trip-based model, but otherwise they look very good, and man, I'd take this model anywhere. Another way we wanted to look at this is to stack up the trip length frequency distributions. So we took the 9 tour purposes in our model, as well as the 6 trip purposes in the trip-based model, and we collapsed them down to these 3 very basic trip types that you see across the top of the chart here. And we did it for the 4 periods that are defined in the trip-based model. And as you can see, the curves are really similar. Where they kind of differ from one another is in the home-based work or the commuting flows, which is there in that center column, where you can see probably the area under the curve looks about the same, for both of them, except for the PM peak, where you see kind of a bulge there, right there at the very short end of the trips. that doesn't really show up anywhere else. And we scratched our heads about this, and then we realized, oh, this is where the effect of the multi-stop work tours, which are very prevalent in the data, are kind of showing us a bit of divergence from the trip-based model. And so you have a lot of trips that are non-home base or home-based non-work during this period as they make the intermediate stops between their workplace and home. And you can sort of see that in the non-home based tripling frequency distributions, and especially at nighttime, where some of these tours linger across the PM peak period into others. We also took a slightly different look at origin destination patterns within a region. Many of you have seen a chord diagram like this before. On the left is the trip-based model, and on the right is the tour-based model. And what we're showing here is we're showing the connections of the trips. And as you can see on the left here in Asheville, in the trip-based model, almost all of the trips begin and end in Asheville. And indeed, that's true for almost everywhere except for Fairview. And that's not a surprising outcome because, as you saw in the tripling frequencies we just saw, the average trip length is relatively short, so you say closer to home. But when you look at a tour-based model over here on the right, you start to see some really interesting interactions there in Asheville. Only about half of them stay within Asheville. And as you can see on the screen, there are a couple of other tours to different places that show up. We see this in activity-based models a lot, where you see a lot more of these interactions between places in the region. And it tells you something about the travel that is sort of hidden in a trip-based model, which is just showing you the aggregate travel patterns. Indeed, it's interesting to note that both of these are robust views of the same population, as evidenced by the fact that the traffic assignment results for both of these are quite similar. But the one on the right shows you some tour patterns that you would never pick up looking at a more aggregate accounting of the data. And we're totally jazzed by what we can see in this. I'm really excited about this. This is one of the coolest things I've seen in 20 years of working in travel forecasting. I could tell you a lot more, but we'd run out of time. So, Josie, I'll give it back to you.
Thanks, Rick. So Rick just reviewed some of the model statistics, and I'm going to go over the development time and cost and usability between both of the models. So starting with the development time and cost, we tried to make this comparison as close to an apples-to-apples comparison as we could. And so to do that, we estimated the person hours that it took to develop both models. And our good friends at PB summed up all the hours that they spent building just the resident trip-based model. And that included processing and analyzing the survey data, estimating, implementing, calibrating, and validating the trip-based resident model. And that totaled 462 person hours. For this tour-based model based on passive data, we spent a total of 75 person hours. That included processing the passive data, implementing the DES, and validating. If we span that out to how much time it would take in a calendar month, we assume that one worker did all the work and they had 50% availability. That equates to 1 month versus 6 months. Keep in mind that the trip-based model also required some extra time to collect the input data on the front end. So in the case of Asheville, it took about 6 extra months to collect the travel survey and about $275,000. In the case of the tour-based model, we were able to purchase the passive data in a week or so, and the total cost of all of that data is much less than the survey alone. If we move on to talk about usability between the two models, the first thing we think about is runtime. And the tour-based model ran in 50 minutes on a MacBook Air, and the trip-based model takes about 4 hours to run on a survey. or on a server. The thing to keep in mind is that this 4-hour runtime includes mostly mode choice estimation. But we want to point out that the trip-based model is estimated in an aggregate zonal manner. So when we increase the number of zones, the runtime increases geometrically. Whereas with the tour-based model, we're estimating the model at the person level. The runtime then will be a function of just the population of the region that you're running a model for, which is very easy to parallelize and something we haven't done yet. We built this tour-based model with R and Python, so it's easy to run the model on a Windows or Linux-based system. And we built the DES so that there's no local calibration at all. There's no calibration factors specific to Asheville. So the same code that we used in Asheville, we can use to build a model in Denver or in Atlanta or in Albuquerque, New Mexico, wherever you might be. And this has all sorts of benefits which we discussed in the research brief, which is linked in the description below. But lastly, we want to touch on the fact that real work begins when we start using this model for forecasting or planning. And we think that when combined with the dynamic traffic assignment model, like, for example, open source MatSim, that these two together will work well for forecasting and scenario analysis. And we also discussed this in more detail in the research brief. We'd like to thank North Carolina DOT and French Broad River MPO for sharing their data and their model. And we'd like to close with this. We built a very simplistic DES with passive data. And there's a lot of room for improvement in this simulation. But based on the results we've gotten so far, where they look very similar to the existing model, we're pretty excited about where this will lead. Thank you.